Alright, going through the third day of our optimization problems. I hope you spent some time last night doing the homework problems I assigned out of the packet, and hopefully before you watch this video you spent some time talking with classmates about those problems and maybe resolving any of the issues you might have had. Our first problem we're going to look at today together is question number 1 in the packet, so hopefully you have that out. And we're looking at how do you find the number that most exceeds its square. So what exactly does that mean, most exceeds its square? Well, if we let x represent the number itself, that would mean x squared would represent its square. And so if it most exceeds that, that would mean that if I took x and I subtracted its square from it, we would want to maximize that difference. So again, this is an optimization problem because we're finding a maximum value. So I find the first derivative of that function, which is 1 minus 2x. Setting it equal to 0, I only get one solution for that, and that solution is 1/2. Again, even though I have one solution, I better verify that that actually is a maximum as opposed to a min. And the second derivative of that function is the second derivative is -2. And so -2 is negative, obviously, so it means it's concave down, and so that means it means 1/2 obviously is a maximum, and its square would be 1/4. And if you subtract those, that 1/4 is the biggest difference you ever have. That's the most that number ever exceeds. Usually the square is bigger. Second problem we're going to look at right now is question number 2 in the packet. And again, try to do these problems before we go through them together. It will really help you instead of just copying down answers. So you see I'm drawing right now. I'm drawing this rectangle inside of a right triangle that has legs 3, 4 with a hypotenuse of 5. And I'm going to have to represent some of these lengths here. So I'm going to call that length x, which makes that length 3 minus x. You know, my width here, you can call that whatever you want. You can call it L or however you want to call it, L and W there. And so in this problem, if I'm going to try to write this all with one variable right now, I'm going to have to use similar triangles. Hopefully you see those similar triangles, the ones up there that have dimensions of x and L, and the one that has dimensions of 3 and 4. So x is to 3 as L is to 4. And remember, L is really 3 minus x, if we remember that at some point. But for right now, I can write L in terms of x. So 3L equals 4x. So L equals 4/3 x. And so now I'm going to try to maximize that area. And so again, remember, L is now 4/3 x, and W is really 3 minus x. So as I plug those in and write it all in terms of x, this is what my function looks like, and I distribute it out, and I get 4x minus 4/3 x squared. I'm going to set that equal to 0 as I find the derivative of it. The derivative is 4 minus 8/3 x. Solving that for x, add it to the other side, multiply by the reciprocal, you get x is 3/2 or 1.5. Find the second derivative of this function. Second derivative is just -8/3, which means this is always concave down, which means that our critical value, 1.5, must be a maximum, which is what we wanted in this problem. And so I know that x is 1.5, and so I can subtract that from 3, so that my width of this rectangle is 1.5. And I can plug that in and multiply it by 4/3 to figure out that my length is going to be 2. Third problem we're going to look at today is question number 11 in the packet. Question number 11. So again, be a good time to push pause right now and try to do question number 11. Another rectangular problem. First thing we're going to do is write our area formula for a rectangle. X times y equals 3200. Solve one in terms of the other. I'm going to say y equals 3200 over x. Again, this is a cost problem, so my cost is like a perimeter problem. So I have two sides that have length x, and each of those sides cost $2 to fence. The other side is my two y's, which cost $1 to fence. Multiply those out and then plug in my 3200 over x for y. This is my new cost function. Now I'm going to take the first derivative of my cost function to try to optimize this problem. That first derivative is 4 minus 6400 over x squared. Again, you have to have a solid understanding of the derivatives in order to do this easily. Set that equal to 0. I'm going to add to the other side and cross multiply. When I do that, I'm going to get 4x squared equals 6400. Solving that for x squared, I divide by 4, take the square root. Yeah, there is two answers here, but the negative answer doesn't really make a lot of sense. I mean, if you want to think about it as a positive or negative 40, you certainly can. But if we get a negative 40 for an answer, that's not going to make much of a sense as a length of a rectangle. So I sure hope as I do the second derivative here I get the answer I'm looking for. Take the second derivative of that function. That second derivative is going to be 12,800 over x to the third. Plugging in my positive and negative 40. If I plug a positive 40 in, I get a positive over a positive. In that case, this is concave up, so 40 is a minimum in this problem. If I plug in negative 40 and work it out, it's a positive over a negative. That makes that concave down, which makes that a max. But remember, I want to minimize the cost here, and so 40 is the answer I'm looking for. And if I take 3200 and divide it by 40, I get 80. So the dimensions of my rectangle that minimize the cost here is 40 by 80 feet. I hope that this optimization process is making sense. Probably the hardest part is getting those initial equations correct. Last problem we're going to look at is question number 23 today. And again, I keep reminding you, it's a good time to push pause right now and see what you can get on this on your own. If you've looked at it, you probably don't like it very much because it's another one of those problems where we've got cones and cylinders, and you're going to end up using similar triangles in this problem again. Again, you don't have to write these with the same labels I have, but in my case, I'm going to call the height of the cylinder h, and so that makes that remaining height 9 minus h. I'm going to call the radius of the cone 6, and the radius of my cylinder r. Again, I hope you can see those similar triangles right there. I'll draw them out for you here so you can see them a little bit easier. You've got a smaller triangle that has a 9 minus h for a height and an r for a base, and you have one that's 9 by 6. So I can match those up. 9 minus h is to 9, as r is to 6. Cross multiply on that. When I work all of that out, I should get 9r equals 54 minus 6h, which gives me h equals 54 minus 9r divided by 6. If you want to simplify that, you certainly can. Get it down to 9 minus 1.5r. Now, remember, I'm working on trying to maximize the volume of my cylinder right now, so I'm using my cylinder volume formula, and I've got it written now, so I'm going to write everything in terms of r. So instead of pi r squared h, it's going to be pi r squared times 9 minus 1.5r. I'm going to distribute that pi r squared through, so it's 9 pi r squared minus 1.5 pi r cubed. That's about as simple as my function's going to look. Here's a good time to take the first derivative right now. Try to find my critical values for this problem. My first derivative is 18 pi r minus 4.5 pi r squared. I'm going to set this equal to 0. Here's a problem where I'm able to factor some things out. I'm going to factor out a negative 4.5 pi r. You don't have to factor it that way. That's just the way that makes sense to me. So when I factor that out, that means I've got a negative 4 plus r equals 0. Set each of those two things equal to 0, and I get r equals 0 and r equals 4. Two solutions here. Again, common sense probably tells us that 0 is not going to maximize the volume of our cylinder, but let's find that second derivative and double check. Second derivative of this problem is 18 pi minus 9 pi r. Setting that equal to 0, sorry, not setting it equal to 0, but plugging in my two radii. When I plug in 0, that gives me 9 pi, which is a positive number, making 0 a minimum, because remember that's concave up. If I plug in 4 right now, I'm going to get 18 pi minus 36 pi, which is going to give me negative 18 pi. Negative result tells me that this is concave down. And if it's concave down, then that makes 4 a maximum. Again, I'm looking for a maximum volume for my cylinder here. So remember, x equals 4, or excuse me, r equals 4. So once I know that r equals 4, I can plug that back in and get a height, and my height is now 3. And now I can go ahead and work that out and find that volume, and when I do that, I get 48 pi, and that should be labeled in cubic units. That's my maximum volume. Again, use these examples. Try to go through some problems on your own. Do at least the following problems from your packet. Problems 3, 6, 17, and 27, or as many as you'd like to be able to do. I mean, I've given you, what, 35 problems in this packet. I've only went through and assigned, a dozen of them or so, dozen or 16 of them these first 2 days, so do as many as you can. See you next time.